Welcome to the e-learning program for products for the treatment of potable water. Here we can see the entire drinking cycle from raw water intake through distribution or storage. Many water plants vary in specific applications, but basically screening, aeration, coagulation or flocculation, and sand filters are normally found in each and every plant. We will look at those in detail in further slides. There are several sources of raw water that are used in the potable water cycle. Many plants get their water from groundwater. Examples of these are rivers, streams, canals, lakes, and reservoirs. They can be locally found or imported over long distances via aqueducts or large pumping stations. Another source of raw water is from the desalination. In this process, the water is either heated or passed through special filters to remove the salt. It's not unusual to use several different sources making up a plant's intake to reduce the time and chemicals needed to treat the raw water. Besides surface, where many of our customers prefer using borehole or wells as a source of supply of water, there is one distinct advantage. Natural filtration through the ground allows for a much cleaner product to be brought into the treatment plant, thus reducing the amount of chemicals used as well as energy to properly clean the water. Once the water is secured from the source, pre-treatment is performed by using large screens to remove larger pieces of debris from the water. Oftentimes the water is put into temporary storage at this point and can be pre-treated with chemicals or chlorinated to reduce process time in the plant. Sedimentation. Waters exiting the flocculation basin may enter the sedimentation basins, also called a clarifier or settling basin. It's a large tank with slow flow, allowing floc to settle to the bottom. The sedimentation basin is best located close to the flocculation basin, so the transit between does not permit settlement or floc breakup. Sedimentation basins may be rectangular, where water flows from end to end, or circular, where flow is from the center outward. Sedimentation basin outflow is typically over a weir, so only a thin top layer, that furthest from the sediment, exits. The amount of floc that settles out of the water is dependent on basin retention time and on basin depth. The retention time of the water must therefore be balanced against the cost of a larger basin. The minimum clarifier retention time is normally 4 hours. After the source water has been screened and has passed through the optional steps of pre-chlorination and aeration, it's ready for coagulation and flocculation. The primary purpose of the coagulation flocculation process is the removal of particles which cannot be removed by sedimentation or filtration alone. These particles are usually less than 1 micrometer in size and are termed colloids. They have poor settling characteristics and are responsible for the color and turbidity of water. An aluminium or iron-based chemical coagulant is added to the water in a flash mixer, where it is mixed quickly to evenly distribute the chemicals through the water. After flash mixing, coagulation occurs. During coagulation, the coagulant chemicals neutralize the electrical charges of the fine particles in the water, allowing the particles to come closer together and form large clumps. The final step is flocculation. During flocculation, a process of gentle mixing brings the fine particles formed by coagulation into contact with each other. Flocculation typically lasts for about 30 to 45 minutes. The flocculation basin often has a number of compartments with decreasing mixing speeds as the water advances through the basin. This compartmentalized chamber allows increasingly large floc to form without being broken apart by the mixing blades. Here are examples of subsystems used in the coagulation, flocculation, or sedimentation. The quality of the water and local governmental requirement often affect the exact process used by a customer to treat their water. The most common type of filter is a rapid sand filter. Water moves vertically through sand, which often has a layer of activated carbon above the sand. The top layer removes organic compounds, which contribute to taste and odor. The space between sand particles is larger than the smallest suspended particles, so simple filtration is not enough. Most particles pass through surface layers but are trapped in pore spaces or adhere to sand particles. Effective filtration extends into the depth of the filter. This property of the filter is key to its operation. If the top layer of sand were to block all the particles, the filter would quickly clog. To clean the filter, water is passed quickly upward through the filter, opposite the normal direction called backwashing, to remove embedded particles. Prior to this, compressed air may be blown up through the bottom of the filter to break up the compacted filter media to aid the backwashing process. This is known as air scouring. This contaminated water can be disposed of along with the sludge from the sedimentation basin, or it can be recycled by mixing with the raw water entering the plant, although this is often considered poor practice since it reintroduces an elevated concentration of bacteria into the raw water. Some water treatment plants employ pressure filters. These work on the same principle as rapid gravity filters, differing in that the filter medium is enclosed in a steel vessel and the water is forced through it under pressure. Advantages: filters out much smaller particles than paper and sand filters can. Filters out virtually all particles larger than their specified pore sizes. They're quite thin, and so liquids flow through them fairly rapidly. They're reasonably strong, and so can withstand pressure differences across them of typically 2 to 5 atmospheres. They can be cleaned, backflushed, and reused. After coagulation, flocculation, or sedimentation, the water is sent to a clarifier for further treatment and conditioning. Tight controls are required as the water nears the final disinfection area. In the clarifier, we must measure flow to accurately establish chemical feed rates, wash water rates, and unit loadings. Monitor mixing and chemical feed systems to ensure proper dosage control. Monitor pH for optimum conditions. Quality tests are normally required almost once in every shift. Some plants may use filtration before disinfection. This is also the most common treatment to obtain fresh water from salt water, desalinization. This is known as reverse osmosis, where the filters trap the salt molecules but allow the water molecules to pass through the membrane, filter. Here are a few examples of commonly used filter membranes. The type used varies on application and customer preference. They include filtration, low-pressure membranes, MF/UF, for turbidity and pathogen removal. Organic removal, nanofiltration, NF, for NOM removal. Inland brackish desalination, RO or NF. Seawater desalination, RO or two-stage NF. Membrane bioreactor, MF, UF, MBR. The final process before storage or distribution is disinfection. This step is used to kill pathogens that pass filters and also improves taste and odor. Typical methods employed are chlorine. Chlorination is the most economical and commonly used chlorine gas sodium hypochlorite, bleach. Chlorine dioxide, chloroamines, ozone, most efficient but expensive. Irradiation with ultraviolet light, which is very efficient. Other methods that you may find are sonification, electric current, and gamma-ray irradiation. From here it is off to storage or distribution to customers. After screening, filtering, coagulation, and sand filters, the water is finally ready for distribution to the user, or can be held in large storage facilities until the demand requires it being released into the networks.